Hello everyone, my name is Deniz and this is my Physics 212 project video. Our project was about atomic emission and solar absorption spectroscopy. So let's start with the first part. In an atom, when you excite an electron, it can jump to a higher energy level state, and when returning to the ground state, it emits a photon with a certain energy. The solution of the Schrödinger equation tells us about this energy, and for example, this figure right here shows the possible emissions for the hydrogen atom, which has one proton and one electron. Since the hydrogen atom is so simple, it only has one proton and one electron, the Schrödinger equation for it is analytically solvable, but this is a rare case. For our case, unfortunately, the elements we have used, the Schrödinger equations for them is not analytically solvable. There are still some methods like perturbation and some approximations so that we can solve them, but they are advanced, so I will not be talking about them. So to analyze the light, we need a spectrometer, and this is our setup. As you can see, this is a phone holder, and we are using the phone to record the light. This is our slit. The slit directly sees this diffraction grating in front of the phone, and this diffraction grating is the most crucial part of the setup. I will be talking about diffraction next. So let's talk about diffraction and diffraction grating a little bit. So a diffraction grating is an optical device with a large number of evenly spaced parallel lines. For example, this here is 1,000 lines per millimeter diffraction grating, as you can see. And these parallel lines split and diffract incoming light into its component wavelengths, so that when light passes through this diffraction grating, each wavelength is bent at a different angle due to interference, so that it creates a spectrum. So this diffraction grating is just like a prism, but it separates light into its colors with higher precision and resolution. So we then wirelessly connected the phone to a computer, and inside the computer we use the software called Theramino to analyze the data. First thing we did was the calibration. So we took a fluorescent light bulb with known spectrum in the bottom, as you can see, and in the software we have these two yellow values here. We can play with them, we can put them wherever we want, so that we match the experimental spectrum to the known theoretical spectrum, so that the spectrometer is calibrated. And to make sure that we were correct, we used the laser. The laser is monochromatic, and as you can see, we have a single peak at around 650, which is the theoretical value of the wavelength of the laser. So we made sure that the spectrometer was working properly. So after that, we went to the chemistry lab and we did the flame tests. So we have these chloride salts of these metals. We put them into a test tube, we dissolve them in some water, and we have a tungsten wire. We dip it inside the test tube and we burn it with the help of this Bunsen burner right in front of our setup. So what happens here is that the electrons are excited and the atom emits certain light. And with our setup, we have analyzed them. So here we have theoretical peaks, the expected peaks to be seen, and the observed peaks. So the difference between theoretical peaks and the expected peaks is that some of the theoretical peaks are really close together, so we expect them to be a single peak, and some of the theoretical peaks are really weak, not strong enough, so we cannot probably see them, so we did not expect them. So the observation and expectation really matched together in the cases of these three elements, but for the cases of copper and potassium, we couldn't really observe a clear peak because these peaks were happening quite fast. The light emission was happening so fast and it was fading away so fast, we couldn't really catch a clear spectrum, unfortunately. So let me show the results one by one. This is for sodium. As you can see, we have a peak at around 578 nanometers. And this is for lithium. We have a peak at around 661. And the surprising thing here is that we have another peak at around sodium's peak. And this is because we had a contamination on the tungsten wire from the previous trial. So we had remaining sodium chloride particles on the tungsten wire, and those burned with the lithium chloride. That was an interesting case. And this is the result for strontium. This was the primary expectation. this peak. And this is just an error caused by the settings of the software. I will not be going into details of this, but this is the primary peak. So let me talk about the second part of the project a little bit. So it was solar absorption spectrum, and this is the theoretical spectrum. And as you can see, there are some dips. These are called Fraunhofer lines, and they occur because specific elements in Sun's cooler outer atmosphere absorb light at certain wavelengths emitted by the hotter inner layers. So each line corresponds to a particular atom, like sodium and hydrogen or calcium. These are some of the lines we were expecting to see. And this is the experimental result. And as you can see, there are some unclear dips identified by the software itself. For example, software identifies 2 dips around here, 2 dips around here, and 1 dip here. There are totally 5 dips in this picture. And but unfortunately, we cannot be sure whether they are really the expected theoretical dips or just a coincidence that the software reads dips at those specific values, because we don't see them clearly visually in the spectrum. So we are limited by what software reads, so we cannot be sure. So in the end, there were of course some general limitations, such as the lights in the case of copper and potassium being so fast, so we couldn't catch them, and like the resolution wasn't enough in the solar absorption spectrum. These were limitations because of we were using do-it-yourself DIY spectrometer, and there's also the slit problem because when you change the slit width, something happens. Like if you choose a wider slit, you get more light, which is good, but you lose some resolution, you lose some quality, and if you use a narrower slit, you get better images, but then the amount of light decreases, which is a really serious problem. So you need to pick a sweet spot between them. So these were the limitations, these were the problems we have been through, but in the end, the experiment was partially successful and partially failed, as I discussed earlier. So that was our project. Thanks for watching and see you in future videos.